So let's briefly answer the question of how do we know that the CO2 that has increased since the Industrial Revolution actually comes from fossil fuel use, like we started with coal and then have graduated to oil and gas and many other biomasses along the way. So natural isotopes of carbon that occur in the Earth system are the C12 with 6 protons and 6 neutrons and atomic weight of 12. So isotope mass is 12 units, and this is the most abundant one with 98.89%. And there is a C13 with 6 protons and 7 neutrons with atomic weight of 13 and abundance of 1.109%. There is a tiny amount of radioactive isotope C14, which is produced by the cosmic rays bombarding the atmosphere, which has abundant amounts of nitrogen, 79%. So N is 7 protons, 7 neutrons. So if the cosmic rays can hit the nitrogen and convert one of the protons into a neutron, then it ends up becoming 6 protons and 8 neutrons. So then its properties, it becomes a carbon molecule with 6 plus 8, so atomic weight of 14 and abundance of 1 part per trillion, so tiny fraction, but it's always produced and is available at that level. So when photosynthesis happens, or when the CO2 exchange with the ocean happens, C14 goes into the ocean and to the hydrocarbon that's fixed by photosynthesis, and as soon as it is fixed and let's say buried as fossil fuel, it begins to decay with a half-life of 5,730 plus minus 40 years. So for about 50,000 year time scales, we can use C14 to track how old the water is, because after it sinks from the surface, it has less and less C14 as it gets away from the surface, or the fossil fuel as it or whatever other hydrocarbon that's buried begins to lose C14. But another thing that happens is fractionation of C13 and C12 during photosynthesis. As you remember, photosynthesis is H2O plus CO2 giving you CH2O, which is a basic unit of sugar or carbohydrate. But energetically speaking, CO2 is easier to absorb when it is 12 carbon O2 versus C13 O2. So any hydrocarbon that's formed is depleted in C13 compared to C12 and C13 in the atmosphere. So when you dig up old hydrocarbon, which is fossil fuel, and you burn it, then you begin to release CO2 into the atmosphere that is depleted in C13 to C12 ratio compared to the atmospheric CO2. So if you increase CO2 in large quantities by burning hydrocarbon that is photosynthesized with C13 depletion, then that signature begins to appear in the atmosphere as decreasing CO2. So here is an indicator of atmospheric delta C13 CO2, which is depleted by about 6.5 parts per thousand. So 1 0 on each side is a percentage, whereas if you add another 0, it's parts per thousand, so it's a smaller amount. And there is gas exchange with the ocean, so the dissolved inorganic carbon in the ocean is has excess delta C13 of 2 parts per thousand, and the soils and photosynthesis take this available CO2 and they create a fractionation of minus 27 parts per thousand in vegetation, and then the soil acquires this hydrocarbon and ends up with delta C13 of approximately minus 27 parts per thousand as well. So this is what allows us to look at the increase in CO2 as mixing ratio and parts per million, which we have seen many times already. This is a bit old, but doesn't matter. So you have the seasonal cycle shown as the planet breathing and respiring, and if you remove that seasonal cycle, you see the clear trend. and we are using so much oxygen to burn fossil fuel that there is a tiny bit of decrease in atmospheric O2 as well. So O2 is measured in per meg, so that you can see is been depleting since the 1990s when the measurements started. So if you put this together, then global emissions increase in gigaton carbon per year is seen here, and the depletion of C13 in the atmospheric CO2 is seen as well, going from minus 7.6 parts per thousand in the 1980s to now minus 8.1 parts per thousand by 2005, which is, as I said, is a bit old, but this has continued, and this is a very clear, accurate, precise, scientific, robust proof that in fact the increasing CO2 is coming from burning of the fossil fuels. And of course you can also look at the depletion in delta C13 at various other places. Here is a longer time series going further from 2005, but now showing delta C13. So again, we are going from about 7.5 or so down now at 8.5 or so, continuing this curve in the same direction. Okay, associated with that, you can see on a longer term as well. So concentration and isotopic composition of atmospheric carbon dioxide, the decrease in the ratio of the carbon 13 isotope delta C13 that accompanies increasing CO2 trends show that the sources are fossil fuel and land use change. So here is atmospheric concentration in ppm now going back to a millennium. So it was basically remaining steady both in terms of the delta C13 per mil, so parts per thousand, and CO2 in ppm. So since the Industrial Revolution, this started shooting up, and corresponding to that, delta C13 depletion started shooting downward. So this shows that again that the emissions from fossil fuel are clearly recorded in terms of delta C13 depletion of the CO2 increased in the atmosphere. Okay. Further proof of that is if you look at CO2 again, but also the seawater PCO2 and and the pH or acidification of the ocean waters, you can see that seawater PCO2 has increased because of the increase in atmospheric CO2 putting a signature into the ocean, and increase the CO2 in the ocean water. What happens? You begin to reduce the pH of the water, which is what we call ocean acidification. So this is different than warming. CO2 is easily soluble in ocean water, so as you increase CO2, the so-called buffering reactions in the ocean of CO2 becoming carbonic acid, bicarbonate, and carbonate, which you can look up in my carbon cycle courses, begin to decrease the pH. So pH, which has been maintained at around 8.1 to 8.2 for millions of years, is now rapidly decreasing, which obviously affects calcium carbonate shell forming animals like foraminifera that we used before to reconstruct past climates by taking them from ocean sediments, because they formed calcium carbonate shells, forams, coccolithophores, corals, etc., when calcium carbonate is supersaturated in the surface waters. But if pH decreases, then CO3 or carbonate ions are used up, and then calcium carbonate is not supersaturated anymore, so they cannot form the calcium carbonate shells anymore. Okay, so this is already being manifest as well. So these are the multiple evidences we can put together, and we will come back and see why people still raise issues about whether CO2 is causing the warming that is observed. Clearly, CO2 is inert, long-lasting gas with a long residence time. Hence, its increase is monotonic, whereas the response in temperature need not be monotonic. And we have discussed this before in the early part of the course as a whole, but I will briefly mention it again just in case you're only using these podcasts for whatever reason. Okay, so we'll come back and discuss that a little bit more to make sure that we understand also that the CO2 that is clearly increasing from fossil fuel burning and land use is in fact trapping additional energy, changing the energy balance, and creating the global warming that we are observing, which is not only in the air but also deeply into the ocean as well. So we'll look at those. Okay.